Well, I think we can start now. Thank you for coming back from your lunch. I hope everybody is okay. Um, well, David asked me to talk a little bit about the role of vegetation in monsoon dynamics and precipitation recycling. These are uh, topics that are not exclusive of monsoon, obviously, but I try to make some links that I hope are useful for you. And I think that's about it. Okay, so the outline is just very brief. Three things that I want to discuss with you. It's I'm going to look at the vegetation, soil, and atmosphere interactions, and well, what you would call feedbacks. And then I will go into discussing a little bit of recycling of water vapor, and some modeling studies that have been done with WRF and other, and well. WRF is particularly important for us because we've been working with that model for a long time. And there's been some developments that are very interesting, and I think everybody that is interested in regional modeling would really welcome these new developments. Well, I chose Africa because I like it a lot, and I think most of my gene pool comes from there. So that's why I chose it. And also, it's a very distinct, has a very distinct response in precipitation during the monsoon um, periods. So the here one here, as you may have seen from earlier um, slides that Simona and Spencer show, how the ITCC is really modulating the precipitation. This is a specific humidity. Actually, yesterday you were introduced to that concept by Simona, so you know how to what we're talking about here. So this is the amount of vapor, amount of vapor in very near the surface. It's almost at the surface. It's 1,000 millibar, and and you can see also the scale. Look at the scale. It has very tiny numbers because it's remember it's a unitless variable, and so it has it's in kilograms per kilogram, and so it has it's very tiny, right? So most of the time meteorologists will multiply this by 1,000 so that they get grams per kilogram, so that is more sensible number. They get more sensible numbers. So that's what it is here. Around here, let's see. This is the month of where is it? I think it should be. This is February, and this is June. Yeah. So it's just one period of from 10 June. This is I took it from Erie here, so you can see the change very clearly from one season to the other. And this is low-level winds. Um, and you can see also, very interestingly, here these convergence zones here that are connected to what we saw before. Here, the monsoon in the monsoon region, this is all desert here, but this part, we want to see what's the response of the vegetation here. You can also see the convergence zones here on on the eastern part of Africa. Remember, this one, this thing is here. So it's collocated with with um, uh, it's collocated with this border between the low low humidity and very large humidity. So it's a very strong latitudinal gradient. And yeah, you can see this in OLR as well. I remember OLR is just it's giving you the energy at the top of the clouds. So this is low energy because they're very cold, and this other part has higher values because this is the desert. And also here, what you see here is basically the ground, right? And OLR is just the outgoing long wave radiation. And look at the same thing is happening. So there are clouds there, and so there is vegetation. There is a precipitation, but there is also a response from the vegetation. And this is just a schematic of what we just saw. And look at this line is the border. It has to do with the changes, latitudinal changes of the intertropical convergence zone, as we saw before with our colleagues. Um, so we can look at how to detect how vegetation is responding to basically radiation and humidity. Well, uh, people have devised this index, which is the NDVI, the normalized difference of vegetation index, which tell us if the vegetation is healthy enough. If it is, then it absorbs most of the visible light that hits it and reflects a large portion of the infrared light. Unhealthy or sparse vegetation, and you can see this. This is kind of it's at the wilting point here for the for the plant, and then it reflects more visible light and less near infrared light. So if you get the difference between those two, between measurements of infrared and visible light, then you get the so-called NDVI, and you can and this is the near infrared minus the visible, and then you divide by the sum to normalize it. So that's why it's normalized. There is another interesting index. I'm not going to talk about it. It's called EVI. It's Enhanced Vegetation Index, but it's very similar. So you can see here how this works. So you have here that near infrared radiation is much larger than the visible one here, and divided by the sum, you get 0.72. So that means it's kind of healthy. And look at this one here. On the other hand, it's almost the same infrared, near infrared, but it has absorbed far more of the visible light. So you get a smaller number. Oh, sorry. Try help. I hope the polarity is okay. Let's see. Maybe not. Alejandro is a much better person for that. Well, anyways, so see this. You see these two values then that reflect different stages of the vegetation. Next one, please. La siguiente, por favor. Okay. Gracias. Thank you. Here you can see on the left a measurement of NDVI, which is a mean annual, and it has a nice correlation with mean annual rainfall. So it means then that there is a connection between vegetation and rainfall, right? Because NDVI measures how healthy or how unhealthy is our vegetation, right? So that means that there is a connection with vegetation. So this is a work by a group of French guys, and they did this for West Africa also. This is how then you see the NDVI behaving during the monsoon periods. On the left, you have the NDVI as we just defined it, and it's for every month of the year from the climatology obtained from 64 to 2020. And then you have the same, but this is just the standard deviation, which tells you how variable this is. Closer to home, well, we have the North American monsoon, or maybe we should call it the Mexican monsoon now that everybody wants to be orange. Let's call it just, doesn't really matter. Well, and the thing is that Carlos Lizárraga from Hermosillo at the Unison, he did some work on NDVI, and he saw what you saw earlier about how this tongue of humidity is actually going up to Arizona, and he measured that in terms of NDVI. So these are the points. He started with, I think here in Tepic and CH, and then TV, RT, and Y. So that's how he wanted to see when was the initiation of NDVI growth. So that's how he characterized how vegetation was actually responding to the monsoon. And these are the results. So remember, CH was the southernmost point. And here we have, it's like this. It's this one, right? So it comes here. So it's the very first one that shows this kink here very early in the season. This is Julian days. So 120, it's like May, and then it starts here around. Well, so you can see here that this kinks is changing as the monsoon develops. Then you have these kinks going further and further into the year. Okay, another change that was tremendous for Mexico was on in the 2023. We have Guerrero, which is this state here where Acapulco is, and it took a very hard hit from Otis. It almost destroyed half of the city, and well, this is the track. But the interesting thing about this is, what do you think is interesting about this? Do you have any? Huh? Yeah, but how about we've been talking about NDVI already. So what is the connection then? Huh? Adrian said something. Yeah. Like about this. This is before it hit. This is after. What else do you see? It really did. It destroyed a lot of the forest that surrounded Acapulco in the mountains. It was incredible. But the thing is that I don't know. It might be just coincidental, but how about? Oh, sorry. How about this and this and this? There are more clouds where there is more vegetation. So there is something there, right? this may not be statistically significant. That's an interesting test that you can check tomorrow or Thursday, Friday. Maybe we can ask Adrian, please give us this data, and then try to publish a paper. So there is obviously a relationship between vegetation and precipitation, but vegetation is limited by the amount of what? What do you think limits the growth of vegetation? The soil, moisture, of course. That's the most important. I think it is there, right? Soil moisture. Yes. So this is something something you can obviously imagine that is happening. This is a relation. Look at this. This is precipitation. It's a sample of only 8 days composite. And the data that they're using for the land is TRIM. TRIM is a satellite product that tells you if it's raining or not. It gives you actual amounts of precipitation. I don't know how good they are. Maybe my colleagues know. Christian knows, and Alejandro knows how good TRIM is. You do, right? No. Okay. I'm not too sure. But anyways, it is at least a proxy of a good proxy of precipitation. But then you can also take a look at what SMAP says. SMAP was a satellite, or rather, it's 2 satellites that measure the amount of moisture in the land, because water changes the distance between those 2 satellites. So it's because of gravity, because it's the amount of water that it's in the land that can be measured. Unfortunately, 3 months after it was launched, one of the most important sensors was lost. But it's still, people were able to get stuff from it. So you can see here that the amount of water, so obviously you have here a lot of water in the Amazon region. You can see, since it's April, it's like in a inter. It's not the eastern monsoon is not yet developed completely. Well, it may know. I'm not too sure here if it should be what part of the cycle or the monsoon cycle are we here? Well, it's May. It's April. I think it's gonna be the eastern monsoon later on. But anyway, so we can connect soil moisture with um, with vegetation very easily, and precipitation. Well, this I took from a very nice review from Sonia Seneviratne. She's a soil physicist at Zurich. This paper has like 4,000 citations. It's amazing. That woman is incredible. Well, anyways, so what we can do is have a measure of soil moisture, and that is this theta. Like Simona reminds us, there are more variables than letters in the alphabet. So, okay, we revert to using theta because it's not potential temperature, please. It's just soil moisture. So, and it's unitless, and it's a measure of so it's cubic meters of water divided by cubic meters of soil. So this definition can be applied to a few cubic centimeters or to several cubic kilometers. But there are some problems with this quantity because there is enormous amount of variability, spatial variability in depth and in the horizontal. It's amazing how soil moisture can change in so small amount of distance. There are several techniques from microwave remote sensing, like I show you in this map. And then there is these TDRs. These are actually instruments that you plug into the soil, and they are really like an antenna. It's an antenna, and so the amount of moisture in the soil will change the times of between pulses, between electronic pulses. But this is a very point-wise measurement. So you have to dig in and then put inside your instrument, and it's a real mess. I've done it. So what we have here is so these A and B are examples of the volumes that I told you before, and this part is unsaturated. We call it also Badeau's zone. It's the unsaturated soil zone, and the first the first meter is the root zone. Although in the tropics there are trees that can be up to 5 meters or even 10 meters. They're amazing. So these are strategies that are very different from that vegetation adopts from in the north or in the south. They change. They change a lot. And so we have the water table um, down here. Oh, and it's saturated basically. So this is our first exposure to what would be some kind of a schematic of the interaction between the vegetation and the soil. We will see more of that. There are some other indices that we have defined, and for instance, we call this the volumetric saturated volumetric soil moisture, theta sat. And it's also called water holding capacity. It's a measure of that. And this theta S varies between 0 with no moisture and 1 when it's fully saturated. Not in the sense of atmospheric saturation, please, but it's close actually because we're measuring moisture in that column. We have several other measures. It's called absolute water content. This is what we usually use in models and in a practical operation of measuring soil moisture. Here's the other one. So we go from 0 to theta sat multiplied by d, and d is a suitable depth that you choose. um, so we saw this, the ratio of saturation. There is volumetric water content, just as is, theta. And there is another one which is called soil moisture potential, which that is defined in terms of the energy that you need to extract from the matrix of the soil. So it's the amount of energy that you will need to exert to get the water out of the soil, which is very important for plants because they need to have energy to get it out. And then there is the soil moisture index, which is a normalized measure of soil. Fine, here in the bottom, SMI. So theta wilt is the wilting where you cannot extract anything from the soil because it has so much energy. You will spend a lot of energy to get it out. And FC is the theta FC is the field capacity. So this is another measure of soil moisture. Okay, so now we have to do some physics here in order to understand a little bit more. On the left, we have the water balance. S is the storage, which will be theta D, like the absolute soil moisture content that I told you about. And D is the soil depth with constant cross section. So now look at this. So we have an amount of water coming from precipitation entering this part, the unsaturated um, uh, soil. And from the soil, we have evaporation, but we also have evaporation from the tree or the plant, which is, we call it evapotranspiration. So we have two modes of evaporating or getting rid of the water in the soil. So this is and there is also runoff. When the soil is too, has reached fill capacity, it cannot hold more water. So it has to get it rid from other means. That means is runoff. And finally, there is a runoff to the ground, which most of the time we just set it to 0. And on the right side, we have the energy balance, which we also know. Simona gave us what a very detailed way of getting this. So the amount of heat storage in this layer of soil is depends on how much shortwave radiation is getting and how much is reflecting, which is the albedo. It depends on the albedo of the soil. And then there is water that is evaporating here. You evaporate here, but LDO, this is the amount of water, net amount of water, multiplied by the latent heat of vaporization that Simona told us about yesterday. And then there is this SH, which is the sensible heat flux. So we have latent heat flux here, lambda E, and this is the amount of, sorry, this was the amount of, I don't remember exactly here. Okay, so I have the first equation, which is the balance, which is telling me how much is how much soil moisture is being stored in the layer, and his precipitation is positive, obviously. Then minus evaporation, minus runoff, and minus the runoff to the ground. So, ds dt is the change of water content within the given layer. And okay, that's it. I think I've explained everything. Oh, right. Oh, it also includes absolute content, which is well, we know that. Let me see. It encompasses additional forms of water storage, such as surface, water, snow, ice. So, so water can take all forms here, all phases here. And this is the land energy balance. So net radiation, which is the incoming short wave. Here at the bottom you have it. Short wave in minus short wave out plus long wave in minus long wave out. That's your amount of available energy at the surface. And then you have to get rid of with a minus sign, lambda E, which is the sensible heat flux, also, I mean the latent heat flux, minus SH, the sensible heat flux, minus G, which is a ground heat flux. Usually we set it to 0. In classical hydrology, we distinguish two main evaporation regimes, and these we characterize via this EF, which is the this fraction, evaporative fraction, which is lambda E, which is the sensible latent heat flux divided by the net radiation. So we have two modes. One is soil moisture limited regime, and one is energy limited regime. In the energy limited regime, values of soil moisture content lie above a given critical soil moisture. This is, let me show you here. So here you are between theta wilt and theta FC. You are between these two. Your values are between these two. Then you are in that regime. So in the energy regime, you are in the energy limited regime, and then you lie above a given critical soil value, and EF does not change. This is what happens here. So you have here, you reach here theta critical, and beyond that, you 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 see no change in your evaporative fraction. It's just, and we say that this is only energy limited. Below the wilting point, you have no evaporation because you died, basically. It is between these two numbers, theta wilt, the wilting point and the critical point, that you can have variability in the evaporative fraction, and thus soil moisture is controlling, or rather, soil moisture is varying due to these. What I mean is that the evaporative fraction is changing according to soil moisture. So there is a source of variability there. These are the first conceptual models of land atmosphere interactions, which consider soil moisture for evapotranspiration, and we distinguish radiation limited regimes and soil moisture limited regimes. The most simple representation is what we call the bucket model. So this guy wasn't given the Nobel Prize because of the bucket model, but he did invent that thing. He was one of the first persons, atmospheric person, that realized that he had to deal with vegetation and soil. This is how you build such model. First of all, you say that your evaporation is a fraction of what we call potential evaporation, which I'm not going to be dealing with this. It's just imagine that you have like a tank, and then you have this evaporation tank, and given you leave it outside and then measure the amount of water that is being evaporated. So this is something that you'll be measuring if you want. But this beta is the interesting one. Oh, by the way, the potential evaporation is just being given by the saturated humidity, specific humidity at the temperature of the surface minus the humidity at certain height, R, and which doesn't have to do anything with this. This RA is a resistance, or the inverse is a conductance. And so it's just a term that tells you how difficult is to evaporate. Beta now is connected to soil moisture, as you can see here with this normalized form, where theta is changing from the wilting point and the critical point. So that's how we connect then our soil moisture with evaporation, and then evaporation with precipitation. So there's a clear link there. Here's Manabe's bucket, a real bucket. And as I told you, these are conductances here. G. For sensible heat flux, you have a conductance that depends on the temperatures at different heights. And latent heat flux also depends on a different height. So you come up with two formulas, which are, we call it bulk formulas, because they are just remember, these are turbulent fluxes, but somehow we're just we're just parameterizing those in terms of the differences in temperature and differences in, also in temperature here. Okay, so here's the bucket, and it's part of the hydrological cycle. Another important characteristic that vegetation has is the so-called leaf area index, and that's the measure of the amount of foliage that the plant canopy has. So if you project if you shine a light on a tree, for instance, from top, then it will cast a shadow on the ground, and it is the area of that shadow that you will measure. So a square centimeter of ground covered by a leaf with an area of 1 square centimeter has a leaf area of one. But if you have two leaves, one on top of the other, then you will have to take into account those two areas. So you will double the leaf area. So you can also do it one-sided. So for instance, needle leaf trees, which are very thin leaves, the total area is no more than twice the projected leaf area, for instance. Also, when you have forests, you have to talk about the big leaf area. So that's how you take into account big communities of plants. Another thing that is very important, and as I told you, sensible heat flux and the evaporation flux are really turbulent quantities, and we measure that. We use Reynolds correlations to get this defined by turbulent eddies. So these are our eddies here, and they will be able to transport very efficiently momentum towards the surface, and also transfer heat from the surface in a very efficient manner. That's why it's turbulent, because otherwise by conduction it will be impossible to do the job. So there is a shallow layer that Adrian talked about, and is like the surface layer. And at that layer, the stress or the stress is constant, so that in the end, you have what we call there is this scale of friction velocity. We call it a scale for velocity, and it's defined like this: U squared equals tau, which is the stress, divided by rho m, and it's just the correlation between turbulent vertical velocity and turbulent horizontal velocity. So that is a correlation, or it's if you want to interpret it differently, it's just the vertical transport of horizontal momentum. Okay. So if we are in this layer where the stress is constant, then we can immediately connect the stress with this shear of the mean flow, and this is a common thing to do. It's just linear thinking, Newtonian thinking. So in this way, we have parameterized the stress in terms of mean quantities that we can measure. So if you do that, then you can integrate this, and then you get simply a logarithmic type of distribution and height. Theta m, and why I'm doing all this thing is just because I want you to see that this term here is the so-called roughness length. And that roughness length is at the height at which the wind field is zero. So, for instance, if you have trees of certain height, then the roughness length will be like 1/10 of that height. Or if you have a tall building, you will also have something like that. So, like 1/10 of something. Here are the roughness lengths associated to soil. See is very in terms in meters. So it's 1 millimeter, 1 centimeter, grass, short, tall, crops. All of them have their associated roughness length. So the more rough the surface is, well, the more, you know, the more turbulent it's gonna be. So, okay, so there are some key land atmosphere interactions, and that's why I will talk about surface roughness, albedo, canopy, ecophysiology. This is something that is a little bit out of my 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 domain of knowledge, but so far we have these three things at least. This is taken from the book of Gordon Bonan, and his Ecological Climatology. Is a very important book, and it's on PDF also, so you can get it, and it's very, very informative. It has lots of information. There is also another interactions with carbon, reactive nitrogen, and aerosols, which is something that in our institute they investigate a lot, and also the volatile organic compounds from biological origin. This is part of our department in the institute. Is aerosols and VOCs. Okay, so let's look at some possible feedbacks. For instance, let's decrease the surface roughness. Okay, so let's reduce soil. Where is it? Roughness. Where are you? Well, this is albedo. So let's see. We increase the albedo. Remember that also that I didn't talk about it properly, but albedo is also part I mean, for instance, you have very low albedos for water, ground, nude, that is vegetation, soil without just bare soil will have more albedo than forests, for instance. So that's an important thing. So this is we can later, if you want, we can go through these feedbacks. They are very important. This is decreased roughness. So you see all the impacts that can have in basically precipitation, convection. Also, if you have deforestation, then you decrease the leaf area index, and then you get also changes in evaporation. Anyway, so now you've seen before what's the hydrological cycle. I'm gonna not, this is just a cartoon, but basically I just want to tell you more about the recycling problem. And of course, there's lots of interaction between the surface, the ocean, and the atmosphere. And here is one part which is interesting enough. Here's the transportation or the advection of moisture in a horizontal manner, where you have also condensation, you have precipitation, you know that. So let me go very fast on this paper, which is an important paper. It builds upon previous work by other colleagues, and that did something similar. And what we really want to see or to do is to understand how much of the evaporated water vapor goes into the precipitation that we receive. So is it that all the evaporation from the soil goes into precipitation? That's one question. Is it? If we evaporate from certain place, will it return to us in the form of precipitation, all of it? That's That's the problem of recycling, right? That's the main problem. So Trenberg simplified this a lot. Also, this is it's a long line of models that have been used in the past to get this important. Why is it important? Because it is a measure of the feedback that there is between the soil and the atmosphere. So for that, then consider flux that goes into this control volume, and F in is what it goes in, and F out what goes out as flux of water vapor, and F is the mean between F in and F out, and E minus P is it would be the amount of mass that is kind of retained inside the volume, and we're not sure how much of it will be admitted out and how much of it will stay in. So for that, consider then the difference between the fluxes out and the fluxes in is simply E minus P times L. It's L because it's the size of the control volume. And the average horizontal moisture flux through that box is given by that. And you can do the algebra, it's very simple. Now we're gonna make a different, we're gonna separate precipitation from two sources. One is the advected one, and one is PA, and the other one is the one that is associated with transport, with horizontal transport. Well, I mean, is the one associated with the local evaporation. Sorry, A is the precipitation, the advected precipitation, and PM is the one that is associated with local evaporation. Then, if you go back to this formula here, then you can substitute PA by PA plus P M, and then the horizontal. If you take the average of that flux in the horizontal, then you get F in minus 1/2 of PAL, and this part is I'm still working on it here, but take it for granted. That part I will discuss with you later because I had some problems with that. But at the end, what you want to do is you want to posit that the atmosphere is well mixed. So that's a very important hypothesis from all these models. So that the ratio of precipitation that falls from advection versus local evaporation is equal to the ratio of the average advected to evaporated moisture. And so it's PA divided by PM, and this is the stuff that we had before. Yeah, this is this one here. It's the advected moisture, and this one here is the one that is the local evaporation. So you get these two, this ratio, and with a little bit of algebra, that one I did. So you get this one. You get this. You can show very easily that the ratio is 2 times the flux in flux divided by evaporation evaporation multiplied by L. So then you get the delta is the actual recycling quantity that we want to look at, and you can end up with this formula. All of these you can use, and in fact, Trembert use it for with reanalysis data. Another interesting, important index is the intensity of the hydrological cycle, which is the ratio of precipitation times L divided by the flux, the average flux in the box. Another one is the moistening efficiency, which is the evaporation times L divided by F. So you can get the recycling ratio and in terms of the moistening efficiency and the intensity of the hydrological cycle. This is how they changes on the y-axis. You have evaporation. On the x-axis the flux, and then you can see that when you change the length of the volume control volume, then you can see very dramatic changes in for the same. For instance, here for 4, which is 5 here, very close to this one. These are very different numbers that you get for evaporation and fluxes. So he did this for NCEP data, and then this is intensity of the hydrological cycle for the winter, or boreal winter, and the boreal summer, and also for this, May. Yes, this is spring, and so there's a different response of intensity according to the time of the year. The moistening efficiency also changes quite dramatically, and the recycling ratio, which is the stuff we were after. And here you have it's very clear our African monsoon is there. Also, the Asian monsoon is there. And Mexico, it has something kind of weird there in the southern part of Mexico. Okay, so these things have been used with global models and also regional models. The majority here is for global models. So they've been using these almost exactly the same type of models, which rely on the fact that well, they rely on the hypothesis that everything is well mixed. So that's one of the real problems. Until here in the bottom, Gonzalo Miguez, he was one of the guys that put water vapor tracers so that we can get rid of that assumption. Yeah. Oh, thank you, thank you. So we can get rid of the well mixed assumption, which is very good. And also, I must tell you, the code is for public consumption, so it's okay. Now, one of the things that WRF has is this coupling to the NOAA mix physics. It has a lot of physics for the vegetation and the soil, and it's one of the best land surface models that we have. ¿Cómo se llama ella? Francina, yes, yes, yes. Yeah, she's Colombian. Francina Dominguez, she's in Illinois. And so they did this for recycling for the Amazonian. And they found, well, first they found that the recycling ratios for most of the models are are okay. I mean, they are very robust numbers. They are in the same the same number. So I think this is very good, despite the fact that they're very limited. So soil moisture is a key player in monsoon climate variability. I hope you're convinced of that. Uh, and results from simple recycling models seem robust in some regions, but have troubles in mountainous areas. That's something that Trember discussed in his papers. We should include not only water vapor as the sole water vapor transport, which is something that they do in these models, but also we need to include the condensate. And we need to understand how soil physics contribute to drought and flooding. Those are some of the things that I think we need to explore. Thank you.
Has time for a few questions.
Okay, thank you so much. Very interesting talk. And I have one comment and one question for you. First, the comment. In 2012, there was a tropical cyclone named Jovan. Jova hit Jalisco state. But the interesting thing about it is that Jova completely disappeared when it hit Jalisco because the whole country was experiencing a prolonged drought. So it was very interesting for me. That's the comment. And the question for you is, so I'm trying to understand this topic. So, in your words, how is the role or the importance of having soil moisture to produce convection over the non-region? It's just because the first rains provides enough soil moisture to begin initiate a deep convection or something like that? I don't know.
Yeah, I think that's something. Well, thank you for your comment. But the and well, in the first for the first comment, that's also another area of research right now. In that heated soil also it perpetuates downwind the this desiccation of soil. So it perpetuates drought and moves it away from the original region. So that's something that needs to be explored also, I think, regardless whether you are in the monsoon or not. But yes, of course, in the monsoon, it's going to be affected. And the second part of your question was that uh, that's very difficult because, as you know very well, the precipitation in the NAM depends on many things. And I think soil might be playing some role there. In fact, Francina worked with the WRF, and she was able to see that the recycling factor was around 10%, something like that, which can be important. But I'm and there are other things that I mean, and like the synoptic conditions that you really talked about before, and I think it might be able to modulate in the long term if you take like decades of data, then you will start to see some kind of signal, I think, from the moisture.
Really nice talk. I have just like a basic question, in particular for the tropics and the monsoon regions. I know that, and I have like zero experience with evapotranspiration or this topic, but how does mangroves, I think is the word in English, how does mangroves react for evapotranspirations? And I know that most of the tropical regions has a lot of mangroves, but there are plants that are like in a super moist environment. So how do they work?
I really don't know about that, but I would say they have no limitation on water, obviously, and they must be able to evapotranspirate as they will. I mean, they can open their stomachs all the time, and nothing will happen because they know that there is unlimited amount of water. So I guess that's a very interesting thing. How I mean, if all the coasts were completely filled with that thing, how would the local regional climate will change because of that? No human intervention, for instance, something like that. Some kind of a scenario like that would be very interesting to look at. Yeah.
Well, first of all, thank you very much for your talk. And my question is related with this thing of predicting. So, which is the best way to incorporate all of this vegetation feedback to the forecast? First, for the nowcasting or this short lead time forecast, and then for the intraseasonal or seasonal forecast. Is it the best way to use some parameterizations or coupling models?
Yeah, well, yeah, that's a very interesting question. As far as the forecasting leading times are concerned, it is from what I've read that the hope is that better knowledge of the soil, the state of the soil and vegetation would actually benefit not short term, but medium term forecast. That's what the literature is saying right now. I'm not too sure at what point they've been able to show that actually, but it is the hope that this will be a very important thing, a very important element in the climate. In the climate already is very important. I mean, Manabe recognized that from the very beginning. Thank you.
Test, test. Okay. All right. Buenas tardes, everyone. I again have the privilege of closing out the day, another marathon day of some really fascinating science of monsoons. So a lot of what I'm talking about today will be picking up on strands that Simona very nicely started us out with this morning in her couple hours. And we'll be touching on stuff from a lot of the rest of the talk so far as well. Maybe logistically tricky with the microphones, but in general, if at all possible, if you have a question we don't have to wait till the very end for questions. Please raise your hand and Alejandro will help me get you a microphone, okay? Because I have less structured activities than yesterday to force you to interact, okay? So it's the ball's in your court, as we say. Okay, and then just hiding the Zoom things on my screen. Perfect, okay. All right, so we'll jump right in. The title of the talk came from a review paper that I wrote, was published in 2019 in Current Climate Change Reports, called Theories for Past and Future Monsoon Rainfall Changes. So there hasn't been too much in the week yet about projections of future climate change in the monsoons, nor of their variations in the Earth's past as recorded in the paleoclimate proxy record. So those are the emphasis of this talk. And the theory part means, of course, how do we try to understand those using the simplest possible analytical frameworks? Okay, so why care about this? This sort of framing is following the manuscript. And I'll just sort of walk you through the line of argument, and then we'll look at each of these sort of one slide each. First, I'm going to argue that monsoons really matter. You don't maybe need to know that. You're here at a monsoons workshop voluntarily, but I'll argue they're sort of from fun scientific and societal angles of that claim. There's a lot of variations, some of it abrupt in the paleoclimate record, and there's the propensity, the real possibility of major changes in the rest of the 21st century as well due to human activities. But in both cases, the uncertainties are really large. And so a lot of actionable information in terms of how to adapt, how to respond in the future is sort of out of our grasp at this point. A big reason for that is that our models, even just for the today's climate, do frankly a pretty terrible job with a lot of the aspects of the monsoon. And how to solve that is going to be a really tremendous scientific, technical, resources, etc. problem. I feel like you can hear my breath. Is that a little better? Good, good, good. Okay, so why are monsoons important to the history of climate science? Well, they basically are what birthed it in its modern form. It was in the 17th century, Halley wrote arguably the first climate science paper. And the whole point of the paper was trying to understand the trade winds and the monsoons. So as someone, I believe Simona this morning mentioned, for the voyagers of this era, the monsoons, what they cared about were the winds that would push their ships around. And so he wanted to understand, come up with an argument for why the trades blew from east to west and why you had this reversing signal in places like the Indian Ocean. And his model was not too bad, actually. It's fun to read that paper, actually. Societal importance. We've heard a little bit about extremes and the damage those cause. I'll talk more about those tomorrow with respect to the Indian monsoon. On a more positive note, monsoon rains in the mean for a summer season drive a ton of agriculture throughout the tropics, right? So much of the tropics, including India, is not irrigated. It's all rain-fed agriculture. And so agricultural outcomes, food production, depends very intimately on how good the summer rains are or bad. We're showing this in this time series from this paper we published in 23. Michela Biasuti is the lead there. The blue curve here is an index of Indian food production for each year. This is going from 1960 to near present. Excuse me, the orange is the food production, and the blue is a rainfall index. So how much summer monsoon rain India got that year. And maybe by eye it's not so clear, but the correlation between these two things is very high, right? So something around 0.7. So you can, how much food India produces, strongly driven by the Indian summer monsoon. In 2010, their finance minister told a reporter that the monsoon was actually his country's real finance minister. He was a puppet, basically. Okay, I snuck this in because of the great question earlier about planetary monsoons. Yes, so Mars has completely dry atmosphere. You might think that's the farthest thing from a monsoon you could imagine. But with respect to the dynamics, the overturning circulation and these rapid seasonally varying, seasonally reversing onset and demise, you have, by any reasonable argument, this monsoonal-like overturning there. So the solar longitude, the x-axis here, is basically, think of it as time of year. You can see the northern hemisphere summer in the middle, southern hemisphere summer in the left. This is stream function, so mass overturning meridionally in the contours. And just focus on the solid red curve is the only one you need to think about here. Really is essentially its ITCZ. There's no rain, right? So this is in terms of vertical, how vigorous the ascent is. And if you recall, it'd be nice if I had overlaid it, but if you recall from Simona's talk, the seasonal cycle for the Indian monsoon sector, for example, of their rains, you get a curve that looks not unlike this whatsoever. So Mars has a monsoon, and then as Simona also mentioned, Titan has essentially a pole-to-pole monsoon system. So this is from a review paper by Jonathan Mitchell and Juan Laura. This is for Titan, the moon of Saturn, going over one single annual cycle, which is about 28 Earth years, something like 30 Earth years, versus latitude, so South Pole to the North Pole, bottom to top. The gray and black symbols are actual observations of cloud features from different instruments. And then the color shading are precipitation from a climate model configured to be for Mars. And you see, so southern summer is this part of the year, and you've got both the model and the cloud observations telling you that the convection is happening basically at the South Pole. And then all of a sudden this jump to convection at the North Pole. And if you look at the dynamics of the overturning more carefully in a Titan climate model, again, it's this very classic sort of monsoonal structure, by and large. Oh, great, already, yeah, Alejandro.
That's, sorry, this perhaps going to be off topic, but perhaps, do you know what is the heating mechanism in Titan? Because Titan is very far away from the sun. So do you know perhaps?
Yeah, so that's actually that connects to what we'll get to later. Yes, the solar constant for Titan is small, right? But it's still a sphere, right? So I think it's like 4 watts per meter squared on average it gets instead of our 340, something like that. But it still gets much more on the part of the sphere that's normal to the sunlight in that particular time. And it has a tilt with respect to its orbit, and so it has a seasonal cycle where you have more insolation in the one hemisphere versus the other, and then in the other part of the orbit, it's the opposite, right? So it's more the gradient rather than the mean value that's crucial here. Oh yeah, and then the fun thing is the rain. Sorry, I'm talking about rain like it's just raining like here. It's the temperatures there are hundreds of degrees Celsius cooler than us, right? And so this is liquid methane. So Titan has lakes and seas and storms and everything like Earth, but the condensable is methane rather than water. Okay, so that's sort of the why should we care part. Now let's talk a little bit about the actual signals in the paleo record and in global warming. But first, yeah, go ahead. I don't think that's on.
Okay. No? Yeah. So for the exoplanets modeling, do you believe that there's like a minimum or a maximum obliquity? I think is the quantity of how tilt is a planet for having these ITC regimes. Do you believe that there should be like an obliquity level?
So Simona has worked on that more explicitly. I don't know that my intuition is it's not a strict threshold per se. I mean, other than if you have 0 axial tilt, that you have no seasonality, right? the more you have, the more seasonal that gets, right? And yeah, that's maybe about all I could say about it. Yeah, great. So Simona will share more tomorrow. Yeah, from your work. Perfect. Perfect. Okay, wonderful. Okay, great. So thank you for taking me up on asking questions. Perfect. Okay, so let's talk about what we see in the paleoclimate record. I'm just picking out basically one single signal here to give you just a flavor. There's ubiquitous evidence across those records of large and sometimes abrupt changes in monsoon rainfall and other monsoon-related fields. This is from a paper in 2017 for the West African monsoon. So this is a proxy record of a lake at 6.5 degrees north latitude within the Sahel. That's the border region between the rainforest and the Sahara Desert. The top red is insolation, going from 20,000 years ago on the far left to near present. And you see that about 10,000 years ago in the Holocene, or the early Holocene, northern summer insolation was higher than it is now. And that's because of precession. So in that period, Earth's orbit was closest to the sun in northern summer and farthest during southern summer. And that's reversed today. Right now, we're closest in southern summer. So during northern monsoon season, the insolation gradient was stronger than it is now. And that basically strengthened the monsoons and enabled rainfall to move further northward into the northern summer. You're seeing that in these proxy records, these blue and gray curves. These are the actual inferred sort of rainfall proxy from their cores that they drilled at this site. I know nothing about paleoproxies beyond basically that level of description in terms of details. But you can see values lower earlier and later, and then this sort of jump up here and higher values during the period when the insolation was higher. The bottom is the same, but from a climate model. So they ran a model, this Trace 21K simulation, where they run it contiguously for a full 20,000 years. And you see, at least with respect to the onset of this sort of green Sahara period, it's called, the model does a pretty good job and it keeps it there. You can also see that the model fails to get this retreat of the monsoon on the tail end, right? So just one example of imperfection of models when it comes to these kinds of things. On the topic of abrupt changes, though, because this is you see this everywhere in the literature for paleo, it's a great way to get a flashy paper. The rain belts in the monsoons, they have very sharp gradients, right? They're a lot of rain is packed into a narrow band meridionally and gets dry very fast afterwards. And we're talking largely about movements of those rain belts. So if you're at a local point and the rain belt is moving even at a perfectly linear speed, right, or a slow speed, the signal locally that your proxy record would record, it will look like a step function, right? So if you're here, it's 0, 0, 0, 0, 0, 0, 0, and then big when the rain belt hits you, right? And then drops back again. So locally, that is abrupt, right? But that doesn't mean that the monsoon as a whole is responding in a abrupt or nonlinear way to the forcing, right? So sometimes these papers unintentionally make the opposite point of what they're, in this case, they have, the proxies here are aligned from north to south, 20, 15, 6 degrees north latitude, and then 5 south. And this arrow is showing, they're trying to convey to you that there's this abrupt termination of the humid period that starts earlier in the north and then later in the south. And this is abrupt, you know, with the scare quotes, right? But if it's just gradually linearly moving south, then it will be abrupt earlier and then abrupt a little later and then abrupt, right? So again, locally, it does, we just need to be, take care when you see and engage with the literature, what people really mean by abrupt. Sometimes the devil is in the details there. Okay, now we'll talk about future climate. Essentially, as I mentioned already, we have possible huge changes in the future, but deep uncertainties. The specific example here is again for the African Sahel. This is from a paper in 2015. Each curve on this time series going from 1900 to the end of the 21st century is a climate model. It's the average Sahel rainfall. And into the future, it's under a high emissions, I think, SSP 8.5 scenario. This is from CMEP 5. And you see, once we go into the future, you have this massive spread, right? So these models highlighted in green tell you that the Sahel is going to get much wetter than it ever was in the historical period. And then you have a model, at least a few that are saying actually it's going to dry out by nearly that amount. A follow-up paper looked at this in the more recent generation, CMEP 6, and it's actually even worse than the CMEP 5 with respect to the spread. I'll talk about this argument about the Saharan air influence in more detail later on, so we'll just move on from there. Okay, another akin to the thing about abrupt, I just want to sort of plant a flag for you mentally. You hear a lot, especially with respect to the future change, about the danger of tipping points. This is sort of a vague notion, but you could think of it as sort of nonlinear thresholds, where once we grow past a certain amount of CO2, the system will respond rapidly, irreversibly, et cetera. It's not there. That's definitely possible, right? There's good reason to be concerned about that in a general sense, but similarly, I urge you to be cautious about that literature. So just one example as regards the monsoons. This is from Buzenstrelmo 2016. Prior, PNAS, et cetera, papers had been published arguing that the monsoons were facing an imminent tipping point, that they were going to collapse under global warming. And if you look carefully at the sort of analytical models that were underlying those claims, they were missing not like small, like little processes. They were leading order terms in the thermodynamic budget of the region, right? Like it was just I don't want to say laughable, but it's just indefensible, right? And moreover, what this figure is in a climate model, Buzenstrelmo subjected this model to a huge range of forcings. So the red dashed, for example, going from 1/4 of present day CO2 in one simulation all the way to 8 times or 16 times in another simulation. Similar changes in local albedo and black carbon, sulfate, and the precip is in the x-axis. For all of those forcings over these massive ranges, it's basically linear, right? So at least in this model, there's no indication of any sort of tipping behavior. Okay, so surely if we can resolve convection, if our models get powerful, or if our computers get powerful enough, a lot of these uncertainties will go down, we hope. Even if we take that as a given, the point of this slide is simply that we have a long ways into the future before the global models can routinely run at those kinds of resolutions. The computing power required is just far beyond where we're at right now. Maybe with AI sort of stuff, there's some chance of us accelerating off that curve, but we can't count on it. And also, Simona is going to talk about this, at least based on, oh yeah, nice. Even if this storm resolving stuff that we're doing, at least these days, we meaning the community, the results aren't always so great with respect to the ITCZ. So even that won't be a panacea, I think. So putting this all together, we have an urgent need for better constraints, and the climate models aren't up to the task. And so what I'm going to focus on as an alternative is coming from a theoretical angle. What are the simplest arguments we can make to clarify our understanding of monsoon responses to external forcing? There's three main paradigms in sort of modern use. And the first is convective quasi-equilibrium. And Simona really nicely covered this morning, and I'm just going to skip it entirely. What I will talk about is this idea of monsoons as local sort of manifestations of shifts of the ITCZ driven by planetary sort of scale energy flows. And then at the end, I'll talk about the moist static energy budget, which Simona also nicely set up for me this morning. And we're going to look at how that can be used in the case of the Sahel again to better understand the response of rainfall to mean warming. Just one sentence to reiterate Simona's points. None of these are consistent with monsoons as giant land sea breezes, right? Monsoons are not land sea breezes. Monsoons are not land sea breezes. Okay. Okay, the ITCZ energetic framework. I'm not going to go into the formalism pretty much at all for this theory because I don't find it especially illuminating. I think just describing it at a conceptual level will be sufficient for the present purposes. If you get really excited about it, you can dig into the papers and follow the equations more carefully. There's sort of a simplest possible explanation and then slightly more involved explanation here. So the first one is if you make sort of reasonable assumptions about energy flows and coupling with the rainfall, you get that the zonal mean ITCZ, its position is driven by sort of hemispheric scale north-south energy contrast. So slightly more detail. If it's provided that your deep tropical north-south transport of moist static energy, column integrated, is predominantly done by the time mean zonal mean circulation, the Hadley cells, and that the ITCZ doesn't differ too far in location from the edge of those cells, their shared ascending edge, then the ITCZ will be coincident or at least very close to this quantity called the energy flux equator. The schematic, if you just focus on the black curve for now, is demonstrating the energy flux equator. This is just latitude in the X and the total poleward energy transport, so in petawatts, say, in the Y. And the energy flux equator is simply where that crosses zero in the deep tropics. And the claim is that in this black curve, that's where the ITCZ is as well. And if the black curve shifted to become the blue curve for some reason, then the ITCZ would shift north to go from the black to the blue circle. Or conversely, if the black curve shifted to become the red curve for some reason, then the ITCZ would shift southward from the black to the red. So you think of the ITCZ as sort of the tail and the energy flows, the energy flux equator as the dog. If that's a saying that it makes sense in Mexico. Like which is the tail, which is the dog, like which is in control. So the key in this framework relating to your question about Titan is hemispheric sort of asymmetry, right? So if we cool, say, the northern hemisphere relative to the southern hemisphere, or vice versa, as opposed to cooling the whole globe uniformly or warming the whole globe uniformly. And the direction, the sort of way of remembering which direction the ITCZ goes is it's intuitive just with convection in general. Convection will tend to go where it's hot, right? So if you warm the southern hemisphere relative to the north, the ITCZ shifts south. and vice versa. If you warm the north relative to the south, the ITCZ shifts north. Very briefly, why does it do that? Like what? Essentially, the further you shift the ITCZ to the south in this example, the stronger the cross-equatorial energy transport will be by the Hadley cell. So it's sort of acting to mitigate against that that difference between the two hemispheres. So a key result of this is that your tropical rainfall, so within plus or minus 15 or so degrees of the equator, becomes sensitive. I should say sensitive, not insensitive, to sort of global energy, the global energy balance, and so you have to care about processes all the way to either pole, right? This schematic from sort of a paradigmatic paper for this framework from Sarah Kang shows that via this sort of eddies thing. So this idea is that the warming and cooling in this example is actually happening well outside of the tropics, but then the eddies communicate that to the tropics, and in turn the ITCZ responds, right? So in the literature, for example, people have invoked this to explain ITCZ responses to northern hemisphere glaciation and deglaciation in the ice ages, biases in Southern Ocean cloud cover and albedo, 20th century aerosol emissions, which mostly cooled the north relative to the south, and the annual mean position of the ITCZ actually being north of the equator. That was the question earlier. If you ask me, the simplest explanation is through this energetic framework, the fact that the ocean transports energy northward on the net across the equator, the ITCZ has to be south so that the atmosphere is compensating to maintain balance. So back to paleoclimate, because of the Milankovitch cycles, this wobbles and wiggles of Earth's orbit and the effects of that on the insulation. This sort of asymmetric forcing in terms of the meridional direction is ubiquitous in Earth's history. And so we'll dive into this framework as applied to paleoclimate now. This to me is like maybe the single biggest success of the energetic framework is applied to the paleoclimate problems. It's from a paper by Toby Bischoff and co-authors in 2017. We'll skip over the details of the model entirely, but essentially we know the factors controlling the orbit very well, and so we know very precisely what the insolation was at any given time, many hundreds of thousands of years back. And so just given that information and these energetic shift assumptions, they come up with this prediction as a function of latitude and time of changes in rainfall within the tropics. And that's what's shown in this black curve. And then you compare that with actual proxy records for a particular site, this one in Brazil in 27 degrees south. You see a pretty darn good correspondence, right? It's not perfect. There's lags, there's all sorts of things that the black curve misses, but it does a nice job. And they show in this paper about many other sites at many other latitudes, southern and northern hemisphere. It's much better than I would have thought that this framework could have done. And this is a point proxy, right? So this isn't like averaging rainfall over the whole latitude of 27 south, right? So this is telling you that local processes matter. We shouldn't ask too much of the zonal mean with respect to any local site. At the same time, there's something there, right? Okay, so now we're gonna turn to climate change. Yeah. Sorry, I thought I had already organized these differently. Yeah, okay, we're good. So that's the paleoclimate story, like the positive version. What I'll just emphasize is in this review paper, I go into much more detail about all of the ways in which the framework can do a terrible job in different paleoclimate problems, actually. So one example very briefly, a simulation of this mid-Holocene Green Sahara period I mentioned in a particular model. You heat the north relative to the south, and the Sahara, you get this movement north of the West African monsoon rainfall. The zonal mean ITCZ goes south, right? So the zonal mean framework is wrong in sign because the zonal mean framework tells you that the ITCZ should go to the warmed hemisphere, and the local monsoon is doing the opposite thing than the zonal mean, right? So this is like putting the best face on the framework, and there's lots of warts if you dive under the hood, so to speak. That's like 5 metaphors rolled into one. But. Okay, so let's talk about climate change. Unfortunately, for global warming, mostly driven by CO2, the energetic framework is just not going to be as helpful, would be how I put it. And that's because the CO2 increase, the extra long wave trapping, it's not perfectly uniform, but it is to pretty good degree, right? It's not like the CO2 is heating the north much more than the south or vice versa. It's relatively symmetric about the equator. And so it's just not innately going to trigger this sort of asymmetric sort of shift response, right? The forcing isn't the end of the story, right? The local response, you could get feedbacks, radiative feedbacks locally, such that the northern hemisphere radiative response is very different than the southern, and you do get a asymmetry. And people have looked into that, and it does matter. I don't want to throw this totally under the bus, but compared to the paleoclimate problem, it's much trickier. So then how do we think about that response to the mean warming, which will be pronounced, right? We know more than anything else that there will be a mean warming of the planet in years to come, and is already commenced, right? And that's instead, well, where we'll find the moist static energy budget framework to be much more useful. So for that, I'm going to turn to the work from my PhD thesis, again about the West African monsoon, the Sahel region. This was all motivated by a paper by Isaac Held in 2005, in which he looked at rainfall responses in 3 different atmospheric models, prescribed sea surface temperatures, and every ocean grid point was warmed by 2 Kelvin. So just a uniform 2K SST warming. And what does the precip do in West Africa in those runs? In this case, the red colors mean drying, blue means increased precip. And you see in this model, AM 2.1, which is the GFDL's model, which is where I was based for my PhD, you get this really strong drying of the Sahel. And in another model, you get a similar thing, is a little weaker. But then in this other model, this third model, yet you get kind of a mixed response, maybe even an increase. So then the question is why? Which one do we trust? I have much more material here than I have time for. So I'm going to take you through, again, more on a sort of schematic sort of level of complexity, our arguments, where we're drawing from the moist static energy budget to try to make sense of why there might be drying under mean warming. In particular, as Simona rightly credited David Nealon this morning, one of the mechanisms he introduced in the early 2000s for precip responses to warming is called the upped ante mechanism. And you can think of the drying of the Sahel at least in these 2 models as basically this upped ante mechanism applied to the Sahel interacting with the Sahara. And I'll spell out what I mean specifically there in just a moment. Suffice it to say, I won't get to these other parts, but just for the number 2, suffice it to say that even within a single model, if you just change the convection scheme, for example, that response, that massive drying response can go away entirely, right? So we can use the MSE budget to try to understand why that is, but it's itself another reminder that the global models, at least as of a few years ago, are the convection schemes are a real Pandora's box. Okay, so this is the sort of our argument in schematic form. Okay, so these up-ante mechanisms, so we're looking actually from the Gulf of, the Gulf is in the right, the Sahel in the middle, the Sahara Desert on the left. So we've kind of flipped latitudes compared to normal. I'll blame my PhD advisor who made this. We have very hot but very dry conditions in the Sahara. We have very moist conditions to the south over the Gulf of Guinea. You have this very strong moisture gradient as a result, and you have flow from north to south from the Sahara into the Sahel. So that's just naturally occurring. So flow along a sharp gradient, that's going to be a horizontal advection, right? And so that quantity will act to dry out the Sahel in present day climate, right? Dry air blowing in from the Sahara. Under mean warming, because of sort of Clausius-Clapeyron arguments, you expect there to be the increase in water vapor to first order to be proportional to how much was at a given location in the first place. So lots of moisture before in the Gulf means that the increase in moisture will be large. Little moisture in the Sahara, then the increase with warming is smaller because you had less to start with. And so that increases the gradient, the difference between the Sahara and the Gulf. And so even if the strength of your winds moving on or acting on that gradient are unchanged, that's going to give you more of an advective drying of this Sahel, this transitional region in between. And so by that argument, in which we formalize with respect to the MSE budget, that tells you that you should expect drying of the Sahel under uniform warming. Okay, so question is, how much more detail do I want to go into? This is text saying what I just said out loud, so we'll just move on, I think. I'll just highlight the Joe and Neela in 2004 was the seminal paper here, along with Held and Soda in 2006 regarding that sort of 7% water vapor increase per degree warming, rich get richer sort of thing. Okay. Let's do this. So Simona introduced the MSE budget this morning. I'm going to jump ahead and say we have on the left, we have the net forcing through your combined top of atmosphere and surface radiative and turbulent fluxes. Those are bringing energy into a column. And in the time mean, those have to be diverged by the circulation for there to be a balance. That's the right-hand side. You can break, if the transient eddies aren't doing much, which we'll say that's fine for now, you can split the right-hand side into a horizontal advection term, this brown, and a divergent term, that's the green. And we tend to just rewrite in the column integral that divergent term instead as a vertical advection. But again, in the column integral, those are identical. So we have the forcing from top and bottom on the left, and then that has to be balanced by some combination of horizontal advection of moist static energy, either in and out of the column, as well as vertical advection, up and down. Okay. One thing to flag here is, alas, the budget framework is very analytically, or it's a very powerful tool, but the nuances of getting it to work quantitatively are incredibly frustrating. In particular, getting the budgets to close when you diagnose these terms is a nightmare. So you have to do these really involved adjustment procedures. And yeah, I spent a lot of dark months in my PhD trying to get that to work. But I have it all. If any of you ever do that, just reach out to me. I'm happy to give you my stuff. We recently got it working again for some folks in my group. Okay, in the classic picture of the deep tropics, going back to Nealon and Held in '87, the balance is simply between the forcing and convection, basically, the vertical advection. Deep moist convection is exporting energy in the net, and that's balancing the forcing. In the Sahel, in the present day, it's basically the opposite balance, or an entirely different balance, where the convection is shallower, it's not doing as much, and it's that horizontal drying from the Sahara, actually, that's the predominant term. So what I'm showing here are profiles in a control simulation and a uniform 2K SST simulation we did in AM 2.1, the same model from Isaac's paper. And the dashed gray is the difference between them. And the quantity, so this is a function of pressure, average over the Sahel. And the quantity is the meridional moist static energy gradient. So dHdy as a function of height. And you can see that with warming, you get a very strong enhancement sort of throughout the troposphere of this gradient. And so that's essentially this up-ante combined with flow. The V part of the advection doesn't change that much, just take my word for that. That's this sort of up-ante mechanism where uniform warming amplifies existing moisture gradients, and so your advection across those gradients gets amplified. That's a map view. I think we can skip that. I just want to show one thing, one last quantitative thing that you can do here. Now we're looking at a sort of a leading order budget with respect to the changes in each term. So the 2K simulation minus the control simulation. In this model, in this region, that budget, the leading order balance is between two terms. It's the overbars are the control, the deltas are the change between the runs. You have this control winds acting on the perturbed MSE gradients horizontally. The sum of those and the changed vertical velocities and the existing vertical stratification sum to zero. That's the balance. And you simply, this is purely diagnostic, but you simply solve this for the change in the vertical velocity within that region. And it tells you that it scales with this changed vertical velocity over the existing stratification. This figure here is vertical velocity. Blue is the control, red is the plus 2K. The dashed is the actual difference between the two. And this is pressure velocity, so negative values mean ascent, positive values mean descent. So you see outside of the boundary layer, throughout the free troposphere, we have this really strong subsidence, right, in the region, consistent with the rain really drying out there. And then the dotted curve is this sort of diagnostic, theoretical sort of estimate for that changed ascent from the MSE budget. And you see that it does a pretty decent job, right? It captures at least the leading order of that descent. That's where I'll stop regarding the Sahel and the MSE budget. The last thing to point out there, emphasize is, this is a very useful tool. It is also diagnostic, by which I mean all of these fields that we're using to make arguments, this prediction, right, of the change in the vertical velocity, it's using fields from the perturbed simulation, right? It's not that I know, so in other words, I'm predicting the change in the velocity from a simulation, from the same simulation in which it changed, right? I don't have, the MSE budget tells you what's happening, but it doesn't directly give you sort of predictions where from the control, you can make arguments for how things will change. You have to invoke other arguments to get to that a prognostic or predictive sort of approach. All right, just close your eyes as I skip through a zillion slides and we get to the end. Okay. Yeah, I just wanted to leave with a couple thoughts, and then Adrian's going to do a little mini hands-on to kind of thing. A lot on this slide, but just focus with respect to the image on the bottom right. This is just sort of more almost philosophical as regards future changes under climate change. There are three different main sources of uncertainty regarding changes in any particular field under warming. In this particular case, this is temperature in Anchorage, Alaska, which has nothing to do with the monsoons, but it illustrates the point. You have internal variability, right? Just intrinsic fluctuations of the system that can change the conditions locally. You have scenario uncertainty. So this is whether emissions go to zero very fast starting tomorrow, or if they skyrocket the rest of the century, or something in between, right? So how does society respond? And then there's the forced response. So for a given amount of CO2 forcing and holding the internal variability part constant, how much warming will you get, or how much precip change will you get, right? And what this paper really nicely showed was at local scales, for example, for temperature at a particular location in Alaska, even going all the way to the end of the 21st century, a huge fraction of the total uncertainty in that temperature change is due to the combination of internal variability, and which we basically can't reduce at all, and the scenario uncertainty. So whether emissions go to zero or blow up, right? Only a fifth or so of the uncertainty in this particular case comes from the forced response. Why does that matter in this case? Is because all of this theory stuff that I've been emphasizing is trying to constrain the forced response, right? We're trying to say for a given amount of warming, how did the monsoons change? So like, this is important, but my point is, don't underestimate the uncertainty when it comes to projections of climate change, especially at the smaller scale, the smaller the scale is that you get to. And I think in general, hydrological quantities are even worse than temperature quantities, right? Okay. All right, very last thing. This is good news, although for some reason people take issue with it. These scenarios, right? It used to, essentially we make these plausible assumptions about plausible futures, right? Whether emissions go very fast to zero, or whether it's this runaway sort of scenario, right? Many of the projections and the headlines you see about future changes, whether temperature, precip, hurricanes, anything, are using these very high-end scenarios. And it was for good reason. Until very recently, those were quite plausible. In fact, maybe that's what it seemed like the trajectory we were on. However, just in the last not even decade, really, there's been a huge uptake in renewable deployment and sort of related things. Lots of things about the real world that I don't understand. The point is that those very high-end scenarios are not impossible, but they're increasingly very unlikely, right? We're sort of, unfortunately, the best case scenarios are also increasingly unlikely. So we're sort of probably locked in for something for middle of the road. Except, the losing the high-end scenarios, that's the good news I was referring to. But sort of, you have to scale in your mind when you hear about projections of the future accordingly, right? Or at least check that they're not based on a scenario assumption that's more or less we can rule out. Hopefully that's a positive note to end on, and I will end there. Thank you.
So
Dave?
Okay, okay, sorry. Did I am I button in on somebody?
No, you're good.
Oh, okay. So, all right, thanks. Well, actually, when I passed by my house, I checked my email, and one of the guys from the convect experiment that we're planning says he's watching our videos. So that's good. I'll mention that tomorrow. Anyways, on monsoon convection. I mean, real monsoons like the North American monsoon. Okay, sorry. So actually, just kind of thinking philosophically, one of the things, like for example, when I was asking Simona about, okay, we can't conservation of angular momentum, that's just not a possibility. There's too much turbulence, too much dissipation, eddies, things like that. Also, just in general, when I did my PhD, I looked at entropy budgets, kind of trying to close it in that way. And one of the most important things is just simply dissipation, which models don't do well because you have dissipation at the convective level, you have dissipation at the surface, mixing. So I'm just thinking when you come to these conclusions, even philosophically, so to speak, as you were presenting more theoretical, how is it we kind of, you limit the eddy part, and then you certainly eliminate dissipation, turbulent dissipation, things like that. The idea kind of being that like if the Earth's atmosphere were a heat engine, the work is basically in thermodynamic equilibrium would be to overcome dissipation, so to speak. I don't know if I'm making my question very clear.
I mean, I think you are, but I would maybe challenge the premise. I mean, the GCMs, right? There are somewhat out of my depth here. I'm not a model developer, but they have, there are there are parameterizations of turbulence, right? It's obviously in the boundary layer, but even, if for nothing else, for numerical stability, right? And then I guess so that's sort of got at a formulation level. More empirically, it's been a while since I've looked carefully, but comparisons of zonal momentum budgets, for example, in GCMs versus reanalyses, and maybe you would challenge the underlying model of the reanalysis as well, but holding that aside, as I recall, they're not crazy, right? So yeah, I don't know. I'm not losing any sleep at night regarding dissipation. I'm gonna wake up in the night and Dave is gonna be in our hotel room. It was worse before the gravity wave drag parameterization. Oh, okay.
Yeah, so I have like a kind of question for your last slide here, and in particular, like for students. I know that a lot of folks that I know they're still working with comparison between like current climate and the S&P, like the 8.5. And normally to get like a stronger response, for example, in the shuriken side, know that usually when you're like in the weak mitigation programs, for example, just polar expansion, you are within the range of like the current climate, and it's just only when you do like these extreme forces that you see like a clear response of of the weather and climate. Do you think that is still useful to doing like research using like these extreme like that are like not like highly unlikely
Yeah,
future predictions?
totally. I think you just need to be careful with how you present them and how you think about them to yourself, right? So the point, I think, rephrasing, I think what you're saying, the stronger the forcing, the clearer the signal of the response is going to be, right? Like um, the larger the signal is going to be relative to the internal variability. And so it's completely defensible to hit the system with a really big hammer as opposed to a teeny one, so that you can, especially insofar as the response is linear in the given forcing, right? Which in that Booz and Strelmo figure I showed, right? At least in that particular case, it was. And then because then you can just scale down to whatever is a more plausible response. So yeah, I think there's I have no problem with that whatsoever, nor frankly of us exploring carefully sort of high risk, low probability possible outcomes, right? It's just, I guess I think is the Hausfelder paper. I think the title of the paper was that what we need to get past is the idea is that the high end is quote unquote business as usual, right? That business as usual is instead much more way down here.
Thanks.
But the parameterization was mentioned a couple of times, and one of the examples was the Princeton model. You said had the strong drying response, and that when the convection scheme was changed, that went away. So, is that due to the sensitivity of the schemes that were used to the kind of, again, the water vapor? I mentioned it earlier. A lot of the bulk mass flux schemes had entrainment rates for deep convection tuned right down, because otherwise they didn't get the right kind of cloud top heights, because of the fact that the excessive entrainment kind of kills off the updrafts. And so a lot of those low sensitivity schemes really don't care that much about what's going on above the boundary layer in terms of humidity. So is it right to assume that when you kind of got rid of that drying response, it was switching for a scheme that had a much lower sensitivity to mid-tropospheric water vapor? And could an extension of that being that one of the kind of litmus tests of a trust in a model might even be the relationship between precipitation and kind of column water vapor?
So the last part, I think that's a very useful diagnostic, right? And sort of going slightly beyond that diagnostic is work from Fayez Ahmed using this B sub L convective buoyancy, which has a sort of an even sharper pickup with precip. And he has a paper out within the last couple of years where they've done this diagnostic in CMIP6 models, actually. So I think that's a totally legit avenue. So this is the result that I was referring to. Brown and greens are the precip change in the plus 2K simulations. The default scheme in this model is relaxed Arakawa-Schubert. And then we just switch with the nameless parameter to this University of Washington, Bretherton. It's traditionally a shallow convection scheme. But changing that one thing, nothing else, you go from this 40% reduction in Sahel mean rainfall to a slight increase. I don't know the details of the finer points you were mentioning regarding the moisture sensitivity in terms of formulation of the two models. Our argument for explaining this difference was much more these MSC budget arguments. So basically, with much shallower convection in the climatology in the UW scheme case, you're basically going to moisten the column. The moistening of the column is going to be less with warming than it would be in the case with the deeper convection. And so that whole up-ante mechanism is just weakened, essentially. It's been a while since I've thought about that part. I think that was more or less the argument. Yeah.
Thank you so much for the talk. I was wondering and what happened with the North American monsoon. I understand after several talks that it's a unique monsoon.
Yes.
It's different monsoon. And so due to global warming and climate change, and of course the increasing of water vapor, so we're expecting in the North American monsoon to have less influence because of that, or we can conclude that probably we need more research to understand what's going to happen in several years ahead. I don't know.
Yeah. Somewhat embarrassed. I think I have to punt entirely. I don't, at the top of my head, have any good sense of what the projections are for the NAM specifically in the future. Anyone? Surely someone in here knows. So the mean projection is drying.
It's almost unanimous a response for drying from global model. But that's where the argument comes in, that when you do include Gulf of California scale processes, how is that going to change?
Right, totally.
Thank you.
Maybe at this point it's time to, Adrian, you wanna, because we're getting towards 10 past.